Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you out on your homework here about magnetic fields and AC circuits. So the first question here is all about magnetic forces, right? And the magnetic force, right, when you calculate it, looks like this. Q, it's equal to charge times velocity crossed with your magnetic field vector. Now, if you're in my Physics 109 class, we're not worried so much about the mathematics of cross products, but the important thing here mainly is the direction stuff. That's the important stuff for us. The magnetic force direction is given by the right hand rule. And hopefully you've seen my video on this, but the force direction you get by taking your right hand, put your fingers parallel to the velocity, and then you, in my video I always say sweep towards the magnetic field vector. Your thumb tells you the direction of the magnetic force, right? So hopefully you've seen my video on doing that. Now I'm going to go through one of these with you and let you try the rest of them. These are about a standard XYZ coordinate system. So if I draw a coordinate system, just like you're used to seeing in algebra class, XY like this, right? Plus I points this way, minus I left, plus J points up, minus J down. And then if we add another coordinate, the Z-axis, right, K is a unit vector that points at you, right? So these are what are called unit vectors. I like to think of them as pointers. They're just mathematical ways of talking about direction, basically. So plus I in this context would mean right, minus I left, plus J up, minus J down, plus K comes right at you, and minus K directly away. So if you're watching this video, minus K is in the direction your eyes are pointing, basically. So I'm going to pick one or two of these here. Let's talk about B here. So the velocity is in the minus I direction. So that means we have a charged particle, and its velocity is this way, to the left. Now, our magnetic field vector is pointing in the plus K. So right now if you're watching this video, take your hands, put them direct so that your fingers point directly to the left. Now the magnetic field points in plus K, so rotate your hand until you can sweep towards the plus K direction. Or in other words, your palm should be pointing in the plus K direction. Right? Your thumb, if you're doing this correctly, should be pointing in this direction, the plus J direction. So the magnetic force direction would be in the plus J. I'm going to let you folks now work the rest of these. Text me if you need more help, right? But they're all done basically that way. The next set of problems. This is the same type of stuff. It's just kind of like different unknowns. I'm going to go ahead and draw my coordinate system here, right? X, Y, Z is at you, right? And then the math directions, remember, I, J, K. Okay, and I'm going to pick one of these here. I'll do the first one. So the velocity of our particle is in the minus J direction. That's, in other words, the minus Y, or down, basically, in this picture. So it's kind of physically difficult to do, but try to put your hand in the downward direction. Now here we're given the magnetic force. Remember, your thumb tells you the force direction. So rotate until your thumb points in the I direction. Boy, for me that is physically really difficult because I broke my wrist a long time ago when I was a kid. And then think about which way you're sweeping, or think about which way your palm is pointing. And it should be in the minus K direction. So the magnetic field vector must point in the minus K in this example. And I'll let you try the rest of them there. I know it's physically difficult. I can make more videos at request if you folks are really struggling with it. Just send me a text and let me know. Okay, moving on here. So this is meant, this one is meant to have you think about a couple things, okay? Start by drawing the magnetic field lines around the bar magnet. And I'll draw maybe one field line for you. All right. Bar magnets create what's called a dipole field, and the field lines run that way. Draw a bunch of them though. Okay, and you've seen that. You can, if you actually just put in field lines of a bar magnet, you'll see what they look like. You can put that into Google or anything else, and I've got videos that showed them. Okay. Do the same thing on the right hand side. And the intention here is like that particle is in the plane. Like imagine the magnet sitting on a table's surface or something. This particle is moving along the table's surface. Then ask yourself, look at the field lines and ask yourself, what is the magnetic field direction at that point? And then do the V sweep towards B. Put your fingers in the direction of that velocity, rotate to your palm is pointing towards the magnetic field, and your thumb will tell you the force direction. And I suggest you do this just like we did the previous problem in terms of a coordinate system that looks like that. Okay, moving along. Okay, so this one is designed to give you some sort of idea of how voltage is and currents are created, particularly AC voltage and AC currents. So this is just meant to be like a wire loop, basically, with a resistor there. This is a velocity vector, though, meaning this loop is moving to the left. Now, these are representing magnetic fields, right? So basically, there's a magnet somewhere, and that circle dot is the way you physically show a vector pointing at you. So the magnetic field direction here, if we were to attach a unit vector to it, would be in the plus k direction, right? Now, this is conducting material. So imagine a positive charge carrier free to move. Now, it turns out in conducting material, the charges that are free to move are electrons, not protons. But it doesn't matter, believe it or not, it'll work out just the same. Whether or not you pretend, you imagine a proton or an electron free to move, you'll end up with the same results. And I would just start with imagining a positive charge carrier, because electrical current is defined around positive charge carriers anyway. This charge carrier is moving to the left. Right, so its velocity also is in the minus I direction, and the magnetic field is in the plus k direction. So do the right hand rule on it. Fingers parallel to the velocity. Rotate your hand until you can sweep in the plus k direction, and your thumb will tell you the force direction on that charged particle. And in fact, it'll tell you the force direction on all of them in this region, right? And that will tell you which way the current is, clockwise or counterclockwise, basically in that loop. And a very important thing that anybody watching this should realize is the movement of the conductor in the magnetic field is what's creating a current and a voltage in that loop. That's a really important fundamental concept of magnetism and the magnetic force. You know what, I think I'll just leave that video. I think I'll just start another one for the rest of the problems. So I hope that this helps get you rolling on those homework problems. Have a great day.